Alright, this video is covering section 1.5, talking about measured numbers versus exact numbers, and looking at our sig figs. So remember, I reserved the top portion of my paper for just kind of some navigation headings, and then we're going to cover our measured numbers and significant figures. And again, this is section 1.5. Oops. All right, so basically, what is a measured number? Not all numbers are equal in science, okay, and especially in chemistry. We have two different types. We have measured numbers and we have exact excuse me, numbers. Okay. A measured number, surprise, surprise, is a number that's obtained by measuring. And people say chemistry is confusing. That was a joke. All right, so measured numbers, something that's obtained by measuring. So an example would be, say, anytime you're going to take temperature. Okay, we measure that by a thermometer. So temperature is measured by a thermometer. Or if we're looking for the mass of something versus weight, okay, mass is what we look at in chemistry. This is basically usually measured by a balance. What's important about our measured numbers, okay, is that they're going to have some sort of degree of uncertainty. Okay, because we are actually measuring them, the numbers can vary depending on the type of instrument that you're using to measure them, the person who's using them, how sophisticated the electronics are, if it's something that's electronic. There are a lot of different factors. So for a measured number, these basically are going to have some sort of degree of uncertainty. And in chemistry, we have to keep track of where this uncertainty is. So they're going to have a degree of uncertainty. So they are going to have all of the known digits. So basically digits that don't have any discrepancy between them. They're very established. And then we're going to have plus one unknown digit. Now, unknown might be a little misleading. Basically, this is an uncertain. Basically, this is where our variance is going to be depending from person to person, instrument to instrument, electronics to electronics. That's what I'm talking about. The last digit in a measured number is going to be one that kind of has some flex to it. Now, a measured number is different than an exact number. An exact number is typically one that's obtained by counting. So an example, okay, you say have, in this case, if you were to buy, say, a dozen eggs, you'd have 12 eggs. And you can count them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Say if you were to buy a box of crayons, you know that there are exactly 24 crayons in one box. There is no discrepancy there. Okay, so exact numbers have no uncertainty. So there is no guessed digit. So when we look at these, basically kind of objects are going to be things that are exact numbers, something that's not counted, it's not measured. So no uncertainty in our exact numbers. Now, going back kind of looking at our measured numbers, okay, this degree of uncertainty where it comes into play. So if we take a look at this image here, this is from figure 7 in chapter 1. Again, these images, anytime that I use an image from your book, you do have access to those files. So if you check the file on Moodle, it will have all of the images for chapter 1 that I'm going to use. Typically what I do in a lecture class is I'll have students write down what they think the measurement is of this, I don't know, what is it, a piece of wood probably. Now, what happens is usually students come up with a variety of answers depending on how well they're able to see it, how far away from the screen they are, et cetera, et cetera. Okay. So for this first one, your value that's going to be written down is going to be different than the value written for the one below. Now, for some of you, you're looking at this, well, these are the look like the same size piece of wood, okay, which might be true. But the reason why we're going to write the numbers down differently is because this ruler has a different known value than this one here. Okay, so for our first one, we're measuring this piece, so we're going to have a degree of uncertainty, so we're going to do all the known digits plus one uncertain digit. So for our first example here, we know that this piece of wood is at least 4 centimeters. Okay, that's not an arguable point. You know that that's going to fall in between the 4 and the 5, so we know our first value is going to be a 4. Okay. Then, since we don't have any lines in between the 4 and the 5, that's as far as we know for certain. Okay. The next value is going to be our plus 1 uncertain digit. Okay. So we are going to estimate, we are going to make our best judgment as to how far in between the 4 and the 5 this piece of wood ends. And that's where a discrepancy comes in. So, excuse me, some of you may say that's smack dab in the middle and would say, all right, I think that's 4.5 centimeters. In chemistry, because this last digit, we already accept that it's going to have some uncertainty to it, this last digit can range. So an absolutely appropriate measurement for this piece of wood could be something like 4.4 centimeters. You could even say it's 4.3 centimeters or 4.6 centimeters. Okay, these are all okay because this last digit can vary. Now for the second one here, okay, now we have a little bit more information. We know for certain that we're still between 4 and 5 centimeters, so we know that this first value is a 4. For this next one, now we have some separation here. We know that we're between the 0.5 mark and the 0.6 mark. So we know Now we have a 4.5 value. Now the next digit is the one that we're going to estimate. Okay. So I'm going to say that's about in between the 0.5 and the 0.6. So I'm going to say that this is 0.55 centimeters. Okay. Now these values can vary as well, just like they did here in this last digit. Okay, so appropriate measurements could be, say, 4.54 centimeters, 4.57 centimeters, and that last digit can vary. Okay, what would be incorrect is if you put, say, 4.5 centimeters. Okay, this is incorrect. And that's because when you write 4.5 centimeters, you are suggesting that that uncertainty lies in the 5. Okay, the uncertainty does not lie in that 5. It lies in the second one. All right. When we get down to this third one, okay, if I asked you to write down the measurement of this one here, go ahead and do that. I'm going to guess most of you put down 3 centimeters. Okay. This is wrong. Okay. Now don't get frustrated yet. Okay. If we wrote down the value, this measurement here, as 3 centimeters, okay, remember that a measured number is all the known digits plus one uncertain digit. Okay. If we only have one digit, that digit is the unknown one. Okay. So by saying just 3 centimeters, okay, that's suggesting, well, we're saying it's 3 centimeters, but it could be 2 centimeters, could be 4, could probably even get away with, say, 1 or 5 centimeters. Okay? But because we have these markings here, we know that this piece of wood is at least 3 centimeters. Okay, so this is incorrect. Okay. Well, it would be more correct if we want to say that this piece of wood, we're saying it's right on this mark for 3. How we represent that is we're saying, okay, this is 3.0 centimeters. Okay. Our uncertainty lies in this 0. We are estimating that this wood ends right on that mark. Okay. We don't have any discrepancy of this 3 here. Okay. Our uncertainty lies of whether or not that's actually lying on the line. All right. So why is this important? Why is this degree of uncertainty important to us in chemistry? Okay, these are important because when we do calculations, when we actually take measurements of values and we start putting them into calculations and using them, we have to keep track of where that degree of uncertainty is. Okay, we have to know where that degree of uncertainty is because some measurements, like this one here, are known to a higher degree of certainty, okay, whereas this one has an even higher degree. Okay, so our 4.55 centimeters here has the higher degree of certainty than our 4.5. These two numbers are very different. They are two different measurements dealing with two different things. Okay? Two different types of measuring sticks. So we have to take it into account and to follow that basically. And to keep track of this degree of uncertainty, in science, so scientists use significant figures. Now, significant figures, big phrase. A lot of times we'll shorthand this to sig figs. Okay. Or sometimes, if say I were grading manually your papers, I would put an S.F or just kind of SF to represent that you're sig figs there. So, what makes a number significant? What makes a number not significant when we write it down? Okay. For that, we have a number of different rules. So I'm going to grab a new sheet of paper and go through the rules kind of one by one. All right, so our rules for which numbers are significant. Our first one is any digit that is not 0 is significant. So if we say have 1.234 kilograms, the 1, the 2, the 3, and the 4 are all significant. Okay. I typically, when I'm showing what numbers are significant and what are not, I'll underline which ones are significant. So this number as written has 4 sig figs. Okay. Now, whenever we have a number that has sig figs in it, okay, these first 3, these are the known digits. And our last one, this is the uncertain digit. So we're still following by the rules established for our measured versus our exact numbers. Okay, for our measured numbers, we have to count what they are. Actually, that's a good point. If I go back to my previous page of notes, okay, for our exact numbers, they have no uncertainty. Okay. So they are actually going to have an infinite number of sig figs. Okay. So this little sideways figure 8, this means infinity. That's the symbol for infinity. So if we were to write down, say, these 24 crayons, okay, we would have 24.000000000 all the way to infinity. Okay, so we'd have infinity zeros. There would never be a guessed digit, which means that we would never have a final digit to that. Those zeros would go on forever. So when we're talking about sig figs, we're talking about looking at measured numbers. All right, so our first rule, any digit that's not 0 is significant, which means the only digit that we have to talk about are zeros. Okay? Now, that's where the tricky part of significant figures come in. You can't see it, we'll put them down, but I have 1, 2, 3, 4 more rules to discuss. Okay, and all of those rules deal with zeros. Okay, so that's the tricky part. When is a 0 significant and when is it not? Okay. So our first rule regarding zeros are the zeros that are between non-zero digits are significant. So if we have, say, 2,006 years. Okay, we know that the 2 and the 6 are significant because they're non-zero. Then we have 2 zeros in between. Those are both significant. So this also has 4 sig figs. Now, here's a rule where zeros are not significant. Okay, zeros to the left of the first non-zero digit are not significant. So in other words, you want to start counting sig figs at a non-zero digit. All right, so I'm going to put 2 numbers down. The first one's going to seem really silly to you and really show you. The second one is going to be the number that always trips students up. Okay, so if we wrote down a number, if we had, say, 16 grams, okay, and I wrote this down like this, you'd look at me and say, what in the world were you thinking? Why would you put those zeros out in front? Right? Those zeros don't mean anything. Those zeros are insignificant. They have no value. They don't change the value of this 16, right? These zeros don't make any sense. So it's just the 1 and the 6 that are significant. Everyone with me there? I'm going to assume by your silence that that means yes. Yes, chemists can have a dry sense of humor, whatever you want. I'm trying to make it entertaining. All right, let's say instead of 16 grams, we had a very small number of grams. And let's say we had 0.0016 grams. Now, it's fairly obvious, right, from our first rule, the 1 and the 6 are still significant. Okay, no arguments there. The zeros out in front are not significant. Okay. So this number still has only 2 significant figures. Now, one way to remember this is to remember that you always want to start counting at the non-zero digit. So you would go down the line. There I have non-zero. Now I can start counting my sig figs. I have 1, 2. Okay. The other way that I look at this is I write this number in scientific notation. Okay. So I'm going to have to move my decimal over 1, 2, 3 times. So this would be 1.6 times 10 to the negative 3 grams. Okay. If these zeros were significant, if they needed to be there, when I transpose this into scientific notation, I would have to write this as 0.001.6 times 10 to the negative 3 grams, which we've already established that putting zeros out in front like that is just silly. It doesn't make any sense, doesn't mean anything. Okay. So, silly. And this is correct. Now, for those of you who still aren't buying it, okay, some of you may look at this number and say, hey, if I didn't put those zeros there, it would change what this number is, okay, which is true. But that does not mean that the zeros are significant in how the measurement was taken. Okay. So our sig figs are all of our digits plus that one guessed digit. Okay. These zeros out in front are just placeholders. Yes, they are there in order to signify the value here, but they aren't significant figures. Okay, and I proved that by writing this number in scientific notation. Okay, these numbers are equivalent to each other. They are no different. They have the same numerical value. Okay, so when we transpose it into scientific notation, in order to maintain those same number of sig figs to make it make sense, we just have the 1 and the 6. All right. Next rule here is any zeros that are to the right of a decimal and a non-zero digit are significant. Now, kind of as it's kind of a separate rule, but not really, but it's going to seem like a separate rule, so I'll just kind of write it right underneath, is that if the number is greater than 1, okay, the zeros to the right of that non-zero digit are only significant if a decimal is present. So I'll write that down and then I'll show you guys an example. So if we look at an example here, if we say have 2.0 grams, the 2 is significant because it's non-zero, and the 0 is also significant because it comes to the right of a decimal and it's to the right of a non-zero digit. Okay, so this is 2 sig figs. If we wrote this number as 2.000 grams, the 2 is significant because it's non-zero, and all 3 zeros are significant as well. So this would have 4 sig figs. If we have a value, say 0.00420 grams. Okay, remember these zeros out in front are not significant. We want to start counting at a non-zero digit. So our 4 is our first significant figure. So we have our 4 and our 2. The 0 to the right is significant because it's to the right of a decimal and a non-zero digit. So this has 3 sig figs. So these all deal with this first bullet point. Oops, sorry about that. This second bullet point, okay, if we wrote this value, we had 2100 milliliters versus 2100 decimal milliliters. To an average person who doesn't know about sig figs, doesn't work scientifically, you would say these are the same numbers. To a scientist, these are 2 completely different numbers. We have in our first value, the 2 and the 1 are significant. So this has 2 sig figs. In the second example, the 2 and the 1 are still significant, but both zeros are significant. So this would be 4 sig figs. These are different solely because of where that decimal is. Okay? Why this is important to us, okay, as scientists, goes back to what we talked about with those measured numbers. Okay? For this first value, the 1 is where our uncertain digit is. So that's where our uncertainty is. In the second value, it's the 0 in the 1's place where our uncertainty is. So this number here, okay, this is a measurement. This could range from 2,000 milliliters to 2,200 milliliters. So that could range. Okay, in this value, our range is much smaller. This could be 2,101 milliliter, okay, 2101. Okay. It's this last digit where that uncertainty is. So as scientists, it's very important to know and understand where that degree of uncertainty is. And we do that, we keep track of that by keeping track of what is significant and what is not. So this was a particularly long lecture, but I want to end with giving you a couple examples to work through to give yourself some practice before you jump into your Q&P and your sapling learning. So basically I want to know how many sig figs are here. Again, go ahead and pause the video and try these out. All right, so our first number, our 7 and the 8 are significant. So we have 2 sig figs. The 6.033, the 6, the 3 are significant. And the 0 falls in between a non-zero digit. So we have a total of 4 sig figs. Our 60 nanometers here, only the 6 is significant because we don't have a decimal, so this 0 is not significant. Over here we have our 0.00002 liters. That only has one significant figure. The zeros out in front are not. Remember, we want to start counting our significant figures at the first non-zero digit. We have our 7 and our 5 are significant. So we have 2 sig figs. And in our last example, the 6, the 2, and the 1 are significant. The 0 between the 6 and the 2 is significant, and the 0 between the 2 and the 1. But the 2 final zeros are not significant. So we have a total of 5 significant figures. So try out your Q&Ps, really practice on when a 0 is significant and when a 0 is not significant, and use your sapling learning to also help you. There are tutorials on there to help you through the process of figuring out what numbers are significant and what numbers are not.